Let us now look at the model of this parallelogram linkage. Here, this red link and this blue link are of equal link length. And this coupler, which is the yellow link, has the same length as the fixed link or the distance between these two fixed pivots. As we see, this parallelogram linkage, when it moves, always remains a parallelogram. However, when all the four links become collinear, there is a possibility that it flips into anti-parallelogram configuration and it does not move as a parallelogram linkage. Again, here, if sufficient care is taken, one may transfer it to a parallelogram linkage. So, to get rid of this uncertainty configuration, it is better to have an extra coupler as explained earlier, and we shall demonstrate it through our next model. Let us now look at the model of this parallelogram linkage with a redundant coupler. As we see, these two links are extended at 90 degree and there are two parallel couplers. Consequently, here we should be able to maintain the parallelogram configuration throughout the cycle of motion. It can never flip back into anti-parallelogram configuration. Let us now look at the model of this 10-link mechanism which has just been discussed. As we have seen, according to the calculation, the degree of freedom should have been -1. But notice that these four hinges constitutes a parallelogram, so does these four, and these four hinges also constitute another parallelogram. And these three triangles, the ternary links, are similar to each other. Consequently, this constitutes a single degree freedom mechanism which is an overclosed linkage which has mobility. It is not a structure. Let us now consider the model of this Kempe-Burmeister focal mechanism which we have just discussed. As we see, including this fixed link, we have 8 links, 2, 3, 4, 5, 6, 7, 8. And this is a hinge where 4 links are connected and all other hinges are simple hinges. Accordingly, the formula said the degree of freedom should be -1. But however, as we see, this mechanism can be moved very easily and there is an unique input-output relationship. That means the effective degree of freedom of this mechanism is 1. That is only because of the special dimensions. If we change any of these points a little bit, this will really become a structure and no relative movement would be possible. Now look at the model of this cross-slider trammel. This is that link number 3 which has a revolute pair with fixed link here. This is that link number 5 which has a revolute pair with fixed link here. And there are 2 sliders, 2 and 4, which are hinged to link number 3 here, and these 2 sliders move in these 2 perpendicular slots. For the special dimensions, as we see, this has degree of freedom 1, and rotation of link 3 produces unique rotation of link 5. In fact, we can see that 2 revolutions of link 3 produces 1 revolution of link 5. That is, one can show that omega 3 by omega 5 at all instants remain half. An example of Watt's mechanism with a binary link fixed, let us go back to our old example of this parallel jaw plier. We hold this lower jaw, that is this blue link, fixed. This is a binary link because it has 2 revolute pairs. Now let us note that this binary link is connected to another binary link at this revolute pair and to this ternary link at this revolute pair. This lower handle is a ternary link because it has 3 revolute pairs, and this small link is another ternary link which has 3 revolute pairs. And these 2 ternary links are directly connected. So it is one type of Watt's chain where we know 2 ternary links must be directly connected. Now, if we hold this lower jaw fixed, then we are holding this binary link fixed. we should also note that this is a binary link, this upper jaw is a binary link, and this yellow link is another binary link. This binary link is connecting this ternary link and this binary link. As a result of this, we get a Watt's mechanism, a Watt's chain. This is Watt mechanism of one kind. Later on, we will see Watt's mechanism of another kind, where a ternary link will be held fixed. Ternary link is held fixed. Let us now look at the model of the Stephenson's mechanism, where one of the ternary link is held fixed. Here we have this fixed link as the ternary link, which has three hinges, one here, one there, and another there. And this is the other ternary link, which is connected to the fixed link by two binary links. So the two ternary links are not directly connected, they are connected via binary links at these 2 points and by two binary links at this point. This is a binary link, this is a binary link. These binary links are equivalent because at one end this binary link is connected to a ternary link, at this end this binary link is connected to another binary link. Similarly, this binary link is connected to a ternary link at this end and to a binary link at this end. So these two binary links are of same nature. Similarly, these two binary links are also of same nature because they are connected at both ends to ternary links. So one of the ternary link is held fixed and we get one variety of a Stephenson's linkage. Let us now look at the model of this 4R chain, where the red link is the shortest link, that is L min, and this green link is the longest link, that is L max. Now if the adjacent link to the shortest link, say this yellow one, is held fixed, and this is a Grashof chain, that is L min plus L max is less than L prime plus L double prime. Now in this Grashof chain, if I hold one of the links which is adjacent to the shortest link, that is this yellow one, fixed, then we get a crank rocker, because the shortest link is able to make complete rotation with respect to this link, whereas this green link only oscillates with respect to this link. So we see that the red link is rotating completely, whereas the green link is only performing oscillatory motion, and we get a crank rocker linkage. Another inversion, if I hold this link adjacent to